our final topic in section 9.2, which introduces exponential functions, is the compound interest formula. All right, and this is the first topic that we're actually going to need the use of our calculator on. Okay. Now, usually when you first talk about interest, like in maybe in elementary school or middle school or something, you deal with what's known as simple interest. And simple interest is really just like a linear function, because simple interest, you're only earning interest on the amount that you started with. So, I mean, you would keep, earning the same amount of interest year after year after year, assuming the rate stayed the same, right? But now with compound interest, right, interest compounded annually, what's happening is we're not only going to earn interest on our original investment, we're going to earn interest on previous interest, okay? So when we have compound interest, we actually need to use an exponential function rather than just a linear function. And that's our formula right there, okay? So the formula is A equals capital C times the quantity 1 plus R to the x power. All right, so you might look at this and you might say, hey, there's 4 variables here. I'm used to just having an x and a y. Well, yeah, there is really an x and a y. It's just that there's 2 other variables here that are actually going to become constants in our function. All right. So what's going to happen is the input, right, or the x, is actually going to be this x, which is just going to be the number of years, and the output, or the y, is going to be this a value, which gives us the amount of an investment, right? Sometimes you see this referred to as the accumulated amount, right? Now, all that really means is it's the amount you started with plus the interest, right? So the accumulated amount is the total amount that the investment is worth after X years, okay? And now the C and the R are going to be constants, right? The C is going to be the number of dollars that were invested initially, okay? And the R, of course, is going to be the annual interest rate, but expressed in decimal form, okay? So C and R are going to be known values. They're going to tell you what C and R are, and you're just going to have to, plug in various values for X or values for A, right? So the input is really the X, which is the time, and the output is the A, which is the accumulated amount, okay? So simple example. Erica invested $5,000 of her graduation money into a bond account that, that is expected to earn 3.2% interest compounded annually. Quick fix, right? That is expected to earn 3.2% interest compounded annually. So what function models this investment, and how long will it take her to have $7,000 in the account? So first, they just want you to write the function. And all you're doing to write the function is using that formula up top. So in this case, she invested $5,000, so that's her starting amount, which is her C value. And then the 3.2% interest compounded annually, that would be your R value, right? In decimal form, though, 3.2% in decimal form is going to be 0.032. So what is the function? The function is just going to be A, or you can call it A of X, right? Or A of T if you want to use T for years. A of X is going to equal C, which is the 5,000, times 1 plus the rate, which is 0.032, to the X power. So that's your function that models the investment, all right? And then what I could do is I could go into my calculator and I could enter this into Y1 and just say, all right, it's 5,000 times 1 plus 0.032, close parenthesis, caret x. So what I could do is I could look at my table and say, all right, so that means I know when I start out I have $5,000. Then after 1 year I have $5,160. After 2 years I've got like $5,325, so on and so forth, right? So it's in my calculator. So now I can answer the question, how long will it take to have $7,000 in the account? Well, first off, when you're asked that question, it's, what are you trying to find here, right? What you're trying to find in this instance is how long. So you're trying to find x, right? If they're asking you how long and x is the time, that means you're trying to find x. So you're not replacing x with a value. You're going to leave x as the variable, and you're replacing the a, or the a of x, with 7,000. So what you're doing is you're actually solving the equation. 7,000 equals 5,000 times 1 plus 0.032 to the x. And at this point, we're not going to solve this by hand because you need to use logarithms for it, which we haven't done yet. But what we're just going to do is we're just going to look at the table. And we're going to say, all right, well, I know my table says that after 11 years, there's $7,070.44 in there. So we can approximate it from the table, and we can say, well, x is approximately 11 years just by looking at the table, right? It's a little bit over 7,000 at 11 years. So that's what we can do from the table. And then if we want to graph this, what we can say is, all right, well, I know my window only has to go from 0 to 11 because I know the answer is somewhere a little bit shy of 11. And that's my time, and my money went from $5,000 to roughly $7,500, right? A little bit higher than 7,000, I should make it, right? So using that window, 0 to 11 and 5,000 to 7,500, that should give me a decent picture of my money increasing over time. And what do I need to do? I just need to put a second function in here, y2 equals 7,000, and now I'll have this horizontal line coming across and intersecting my graph, and that intersection point is what I want. And my precise value would be 10.682, right? So more precisely, we can say that x is approximately 10.682 years. All right, so that would be my more precise answer using the graph. So it all depends on what they're asking for, right? If they're asking you to round to a number of decimal places, then you're going to have to use the graph. But if they just say the nearest year, the table is fine. Okay? So that was your compound interest. And there is one other type of problem that gets introduced in this section, and it actually deals with a special exponential function dealing with a special number, which is the number e, right? It's actually a special base of exponential functions. E is actually known as Euler's number. That's why it's called E for Euler. And it's a special base. And when are you going to use these functions? Again, I mean, if you take pre-calculus, you'll get into this a lot more in depth. But generally, functions with base E are going to be used in naturally occurring growth and decay problems, right? Where things are growing or decaying continuously, right? Right? Because in nature, things are always growing, right, at every instant. So they're continuously growing or decaying. All right? So that's why you're going to use those functions for continuous growth and decay problems. Now in this class, though, whenever you're using these functions, the function is going to be given to you, right? So you see how here they're giving you this function, n equals 1e to the 0.1386t. this is the function that models bacteria growth, right? If a sample of bacteria is doubling every 5 minutes and 1 million bacteria were initially present, the function n equals 1e to the 0.1386t, where t is the time in minutes and n is the number of bacteria in millions, models the growth of the bacteria. Okay? So what they can ask you to do here is they can ask you to say, all right, well, how many bacteria are present after 8 minutes? Well, all you would do is you just plug in 8 for t. So you just say n equals 1e to the 0.1386 times 8. Right? And again, these are the ones you're going to have to use the calculator for. And the nice thing about the calculator is, since e is a very popular number used quite often, what you're going to do is you can do this as 1, and if you look down here above the ln button, if you hit second ln, it does e caret parenthesis for you. So all you got to do is put 0.1386 times 8. So this is e to the 0.1386 times 8, which would be 3.03, let's say. So n is approximately 3.03 million bacteria, right? Because this was measured in millions. So that was that. And then the other kind of question they could ask you, and this one I'm going to give you so that you can actually do it an easier way, if you think about it. If they said, how long will it take for there to be 8 million bacteria, right? Well, you'll say, all right, well, this is just the opposite kind of problem, right? Yeah, and you'd be right. I mean, in this case, they're asking you how long. So when they say how long, what you're trying to do is you're trying to find t. So find t when n equals 8. So what you're really doing here is you're solving the equation 8 equals 1e to the 0.1386 t. All right? But actually, if you go back and look at the problem a little bit, read it more carefully, they tell you that what's going on here is the sample of bacteria is doubling every 5 minutes, and it started out at 1 million. So to get from 1 million to 8 million is actually three doubling periods, right? Because it went from 1 to 2 million, then it went from 2 to 4, then it went from 4 to 8. So if it doubles every 5 minutes, it took 5 minutes to get from 1 to 2, it took another 5 minutes to get from 2 to 4, and then it would have taken another 5 minutes to get from 4 to 8. So 3 doubling periods in this case would be equal to 15 minutes, right? Now, would I have expected you to get that? No, it would be nice if you did, but I wouldn't have expected it. So if you can't get it that way by just thinking about it that way, what you could have done is you could just enter this function now into the calculator, right? You can enter 1e to the 0.1386x as your y1, and then your y2 as 8, and then you can just graph it. Well, actually, we could have even went to the table, I guess, right? We could have gone to the table first, and you can see that at 15 minutes, look how close it is. It's 7.99 6, which would basically round to 8.00, right? So you can see right here from the table that it's going to be almost precisely 15 minutes, right? And if you go back and look, you can see how it works, right? Because at the 5 minutes, it would have doubled, right? It went from 1 to 2, basically. And then at the 10 minutes, it doubled again, from 2 to pretty much 4. And then at the 15 minutes, it doubled from 4 to 8. And then 20 minutes, it's going to be basically 16, right? It's getting further and further off as you go down, because it's not, it wasn't exact at that point. 1386 is a rounded value, but close enough, right? So you get the idea. So that was 3 doubling times, so that would have been 15 minutes. Okay? So those are really just the kind of application problems you would get with exponential functions.